All right, folks, welcome to another live stream. Today, the shortest turnaround we've had between a previous live stream and another live stream, only 1 week. So, covering the same topic again, hit on Markov models. The last two notebooks in the Dynamax repo before taking a long break, as I'll be in New Zealand. So. Today's discussion will be a little bit more freeform, much shorter than our previous discussions, but let's go ahead and jump into it. I'm always fiddling around with the settings, so if the audio or anything is lagged, please let me know. It's a whole procedure to get this all to work. Actually, I should just check that right now. There are so many settings to get this thing to go now. I always have to double check. I think I need a little bit more lag. All right, we should be good. So what I'm looking at here is it's going to be two notebooks that I have put up on our GitHub repo, which I should have brought up. So github.com, K29, SSM Book Club. In here, there are some new things that I pushed. Gaussian hidden Markov models. There's a stock price CSV, and then I updated the notes a little bit. I'm going to be going through this, and then I also will be going through the Jax notebook here as well. So I'll throw that in the chat for folks to look at. So this week we were focusing on closing out the hidden Markov models in Dynamax. So we'll go to our favorite repository. It was these two notebooks, HMM Crossvalidation and Autoregressive. Let me talk through these at a high level. Since this is more freeform, I wanted to ask you folks, were there any questions or anything you wanted me to talk about in particular? Cue those questions up as I talk through these two notebooks. I give you a high-level overview, and then we can focus in on I can see what your questions are, and then I can go through the original work that I did for this week. So previously we had talked about basic HMMs. So the casino HMM was I don't want to say contrived example, but it's a simple example of a sort of classical HMM academic problem. You have two devices that generate random numbers. They're discrete, which makes them easy to talk about and easy to calculate. And the question is, do you flip back and forth between these two dice, and what is the probability? So one was state estimation. One part of the state space model is this part right here, the state, which is where are we going to end up. I believe I'm looking at the right one here. And then state, because that's Z. And then the second part is right here, which is what is the thing we're going to see from the dice roll. So this particular notebook was focused on state estimation. Where are we in with our dice? Which dice is being rolled? And then the second notebook was all about learning the parameters. So instead of just trying to figure out where we are, it's trying to estimate what is the transition probability, what is the probabilities of the emissions. Transition probability being from state to state, so which dice are we switching back and forth, and then emission probability being if we are in a state, what is the probability we'll see a certain dice roll. So this being discrete and all makes it quite easy to talk about and visualize, and also computationally makes it quite simple to, I don't want to say super simple, but makes it computationally tractable. This week we're staying with discrete states, which means that there's only certain states we can be in. but our emissions can be continuous. So I'm going to repeat that one again. We are in a discrete state, so we'll be in one of n certain regions. So 1, 2, 3, 4, 5, 6 sort of states. That's the latent representation of the world. And then the outputs can be Gaussian. And so you can see that in this formula here. This indicates that y is a function of the state and some parameters, and it's distributed as a normal distribution with a mean and then some covariance. And so this is the indication that we will have a continuous sort of output state. Here's the example of them initializing the outputs. Sorry. Here's an example of them initializing the HMM class and then all the covariates and everything like that, the covariances and all that. And then here's what the output state looks like. So what happens is we are in certain regions, we're in certain states, and once we're in that state, the outputs will be Gaussian like this. In this case, they're perfectly circular Gaussian. They don't have to be. They could be correlated or whatever the case might be. But they could be man, it's early for me, so I'm gonna get the words out. As we're in certain states, we'll get emissions that are concentrated around those regions. Theo's asking, are there any real-world examples from the world where Gaussian HMMs are useful? There are a couple. I can talk about them in a second. So we go through this. In this notebook, what we have is we have the simulated data and we have the states. And sorry, Theo's comment about frogs jumping on lilies. I'll pull up the chat. So Theo's talking about frogs jumping on lilies. We can't see the bottom, but is a funny one. So we'll talk about. I'll get back to that in a second. As we're in a state, we end up with emissions that are normally distributed in that state. So here we're in the maybe state blue. We get Gaussian emissions along this line. On y1, we get Gaussian emissions along this line in y2 dimensions, and then we switch to another state, and then we end up with emissions around a certain region. And then we switch to another state, and you see sort of these lines go. And these two lines correspond to the coordinates here. So this yellow here corresponds to the yellow is here as well. So the rest of this notebook then goes through actually a pretty good overview of then how do you figure out how many states there are and cross-validation and a whole bunch of functions. This is maybe we won't say HMM specific, but this is a little bit more machine learning type of curves. This is called an elbow curve. Sometimes you see them plotted the other way. Like, let me pull up this up so you folks can get some interview knowledge. You see this elbow method of clustering or elbow curve, and typically, I guess they did it this way. Sometimes you see it go the other way. Man, let's see if I'm a liar. Oh no, it's right here. Okay, here it is. I know I wasn't lying to you folks. So you see it go the other way, where the loss is plotted this way, the deviation or loss or whatever you want to call it. In their case though, they're trying to maximize the log probability, so they go up. But it's the same idea. You just take a data set, you rerun your model over and over again with more and more clusters, and then you see sort of where the drop off is, or the inflection point is of in your curve. In this case, it looks like the number of values was 3. That's like the optimal amount. In our Gaussian curve, it looks like it's 5, which is great because that's exactly what it was produced by. So that's the rest of this notebook. Then it goes through a whole bunch of visualizations of fitting and comparisons. So this is one example of Gaussian HMMs. And then What I wanted to show you when we talk about Gaussian HMMs is there was not even just one type, but if you look at the Dynamax doc, there's actually a number of different types. So again, in these hidden Markov models, there are a number of HMMs implemented, a lot, which makes me really happy with this library. So we have the regular Gaussian HMM, which has a covariance and everything like that. But then we have a diagonal one where the normal distributions don't have a covariance. They're just you just have the diagonals of the covariance matrix. Spherical, which constrains the covariances. I didn't know what low rank meant, so I have to go read. I always forget what low rank means, so this is another point of reading for me. But the general point being is there are a number of Gaussian HMMs that are available in Dynamax. So that's my quick overview of Gaussian HMMs. I'm going to flip over to the questions now because there were a couple. Theo asks, frog jumping on Lily didn't convince him. Lars says one thing could be stock market returns. Luke says, I tried to model pandemic states with AR HMMs and a model when a time series of PCR testing would go into regular period. All right, let's attack these one at a time. So I also had the same question. Are there any real world examples? I've got a couple that I can bring up, and varying degrees of maybe convincingness that they're interesting. The first one, let me see if I can pull some of this stuff up. Otherwise, I might post one in the Slack. Okay, I can only pull up a couple. So here are the ones that I thought of, and I'm gonna go from ridiculous. I'm gonna go from ridiculous to more real world as we talk about it. Let me refind my notebook. So I'll start with the most ridiculous one that I thought of, but I suppose there's an actual application. You're gonna hear a little bit of a story, so you're gonna have to bear with me on this story. Okay. So there's this bird called a parrot. It looks like this. It's very cute. And they are quite small. So here's a parrot in somebody's hands. They're the smallest breed of parrots. My friend owns a parrot, and she's got one in a cage. And the thing is, you don't know which toys parrots tend to like. You buy a couple, and you kind of get a sense. The thing is, we can't observe the parrot at all times because it's my girlfriend. She has the parrot. We would go to work, and the parrot would be by itself for the majority of the day. Let's say 7-8 hours. So I didn't think about this as an HMM problem until I read this notebook. But we would come back, and by seeing where the bird had pooped, like where its droppings were in the cage. So the cage is 3-dimensional, and there's a bunch of toys, and we sort of place them in different spots. We could then get an estimation of where the bird was, and then from the concentration, which toys it liked and which toys it didn't like. So that's a kind of maybe a gross example of an HMM, but I'm now, if I had measured in the at the bottom of the cage where the stuff was, where the bird's poop was, I could use a Gaussian HMM to estimate which toy the bird liked the most. So that's my ridiculous example, though I'll stand by it. I would guess then the real ecological thing is the same thing could be used in ecology. I think maybe where there's endangered species or animal species, the Gaussian HMMs could be used to find clusters of animals. Like maybe where do they tend to stay in a region? How do they tend to transition potentially between different areas and migration patterns or things like that? Could be the more serious sort of counterpart to that same thing that I was observing, at least in my apartment. So that's one example. Then you folks had actually beat me to the punch. One thing could be stock market returns. Lars says you may have different states, but your returns in each emit a Gaussian. So this is my oh no, did my notebooks? Okay, no, it's the old notebook. Okay, this is what I modeled in the notebook that I'm going to cover, and this is the one that's on my repo. It is stock market returns. So it's actually the Microsoft stock price, and I'll have to say I copied this from, as I was looking across the internet, I found this library called HMM Learn. Let me post the link here. So I found this other library called HMM Learn. The library looks great. It's a very similar library to Dynamax, in the sense that it's about HMMs. I want to say I'm not talking poorly about open source, because open source is always a labor of love and people put a lot of work into it. So this isn't a criticism of the library. It just it's built on NumPy. We'll talk about JAX later and why JAX is so cool. It's built on NumPy, which is totally fine. It does the numerical computation estimations, like the Viterbi expectation maximization, the ones that you can calculate with just straight multiplies and things like that, and it works quite fine. But in particular, I just wanted to see whether I could implement their example in JAX, and that's what I did. So I copied a lot of the code out of here. Full credit to them. And what they did is they pulled the Microsoft INC. I forgot what INC, the INC stock ticker is, but they pulled the I think Intel Chip Corporation. Let's just double check so I say the right thing. Intel. Okay, yes. They pulled the Intel stock data, and then they used an HMM to figure out various states that they were in. So they picked 4 states, and then here are what the states ended up being. This they don't have the original plot on here, so we'll show you that later. But once you decompose the stock price, this is one state, and this was one Gaussian emission. There was this sort of spike in Intel's price, and that was another Gaussian emission. There was a third state that was all these tiny things, and then a fourth state, indexing, that looks basically similar to the 0th hidden state. So one can make an argument that maybe there were only 2 states, because these 3 look similar-ish, or maybe there was 3 in the case that there was a long-term sort of stabilization trend. There was a spike time, and then there was random noise per day. Let's say if we go to Dynamax, we can do the same thing. We can grab all the stock prices. Here's what you get: open, close, high, volume, dividends, whatever. Here's the original time series of Intel's stock. Looks like it was low. We have the what's it called? The original tech stock run up and the web bubble and the 2000s, and then it drops, and then it becomes stable again. And then the rest of this is now just Dynamax. So this one took me an embarrassingly long time to figure out, and I had to go into the code and debug it. But there is you have to convert Dynamax representation from just a straight 1D series to an n by 1 series, and then n by 1 by 1, I believe. So it looks like this. So you have everything in a sort of each observation in its own vector, and then you have a vector of those observations. Once you get this, then it's a cinch to then stick into Dynamax. States number 4, I go through, estimate the parameters of expectation maximization, plot what the states are, and then create the same plot, this time series mask. So a little bit interesting in that, and this is another point that was brought up in the last session, is that expectation maximization can fall into local modes. You're not guaranteed to get the same result. And indeed, I did not get the same result as HMM Learn. I got some of the things are similar, like this state. We got this spike hidden state. We sort of got this latent region, about the same, but if you look, they're not exactly the same. So the results are close, but not exact, and that is just something you have to deal with when you're working with HMMs. That's what's happening here. So that's my rundown of Gaussian HMMs. I see many comments have come in through the chat, so let me read through them and see where we're at. Luke says, I tried to model pandemic states with AR HMMs and predict a time series of PCR testing would go in the epidemic period. So this is a very similar example Luke brings up to this one, trying to decompose a time series into numerous different states. It's the same thing that is shown somewhere in this book. I'm gonna see if I can scroll and find it. But in here somewhere, there is a plot where Kevin Murphy shows time series decompositions the same way. The one thing about going through the book is there are so many plots. Okay, here's an example of a similar sort of thing, and there's another one somewhere as well for change point detection. So these are all change point detection type of algorithms. I do this at Google, so we use HMMs at Google to do change point detection in time series, and I wish I could show you the plots and the code, but I cannot. But it is very useful for time series that are irregular and where the data generating process changes, both to estimate where the changes are. Oh man, I always do this where I pull my webcam up and I'm scrolling on screen. All right, so I do this at Google, time series change point detection, and what I was referring to as well is this figure 29.22, and there's another one as well in the book where there's time series change point detection. So doing it with the pandemic makes a ton of sense. Theo says HMM for pandemics. Let's see if I can. This chat overlay will work. Theo says, what do you mean by epidemic period? I can see how that'll be discrete. It's not controlled by a continuous RT. I'm guessing RT is the reproduction rate, Theo. So let me know if I'm correct. So let me keep reading and then I'll come back to the answer. Same with stock markets. Why would the latent state be discrete? Haha, great example. Sometimes you may have things that are difficult to quantify. The overall attitude of investors based here, so you treat them as unobservable. Oh, and to your question, you can model two states: endemic, stable, epidemic growth. RT is greater than 1. Okay, so you guys are talking about the reproduction rate of COVID. So each period generates a time series with different autoregressive constants. And then you would have discrete states of anxiety, optimism. Okay, so there's a discussion here about whether you can model time series as discrete states. So in my example at Google, actually 100% yes. I know I can because I know that there are particular events that happen within the business that change the time series, and I don't always know when they're going to happen, like proactively. They sort of just happen, and then I need my model to take care of them. So in that case, I can point to a single event and be like, this is why the time series changed. But it just happens to be because I work in an area where I can see the thing that happened and like ask somebody and know that it happened. So it changes. And HMMs make it easier to then have my forecasting model forecast differently depending on the state. So this is a good example where you can sort of, in my case, where you can stack models. You use a state estimation model to get basically this plot. Now we're at the portion of the book club where I need to transition between tabs, and there's some randomness on which tab I'm gonna pick on. Okay, you use an HMM to figure out what state you're in, and then once you have these states, you can then use different forecasting models depending on what state you're in. And the ones I used, we usually have 2 or 3, usually 2, where we say we're in one particular state, so we're going to use one type of forecasting, and then we're in a different state, and we use another type of forecasting. There's another example I will bring up, and I guess I'll post it in the discourse because I can't pull it up live right now. But it is when I am trying to gain weight versus losing weight. So there are periods in my life where I try and gain weight because I'm trying to gain muscle or whatever. I have different goals, physical goals at the time. And then there's periods where I'm trying to lose weight, and I consciously making the decision to switch. Don't necessarily need to estimate the states because I'm doing it, but that's another example where a time series would change depending on the state of the mindset I'm in and what my goals are at a time. And Lars points out that, this was the same discussion I would have, is that with Intel, for instance, we don't know the causal reasons why this switched maybe this way to this way, but as humans we can surmise that this was probably the dot-com bubble, right? Like this was a different state of the world that Intel was in versus the 2000s to the 2012s. Like some different things were happening. Interestingly enough, we know that there was another state right here with the housing bubble crash and whatnot. It didn't pick up on, but that the idea being, as was mentioned, that we may switch from different states, and sometimes we care what the states are, and sometimes we don't care what the states are. So that brings up the last point about statistics is it's just, I think there's a latent question here about inference versus non-inference. Sometimes you may have an inferential goal of modeling different states, and sometimes you just want to have better model accuracy. So in that case, you don't really care why they're different states. You just kind of say, I think there's a bunch of different states, and it helps my model do better, and that's all I care about. I'm going to jump on one tangent because you folks are talking about COVID reproduction, and there's a completely different non-HMM related thing that I want to bring up. But at one point in COVID, near the beginning, I had worked the PyMC. Some of the PyMC team had worked with Kevin Systrom, who's the founder of Instagram, sort of like on this open source project where we were estimating the reproduction rate of different U.S. geographical states using Gaussian process models. We can still find the code online. Let me see if I can open the image in a new tab. This dashboard is now down because it's hopelessly. It would be completely wrong if we were still feeding it. But this was updating every day, estimating the reproduction rate of COVID in different U.S. geographical states, and the posterior probability of the reproduction rate. So for Connecticut, we were fairly certain on this particular day, April 19th, 2020. When was the pandemic? 2020? Yeah, 2020. So April 19th, 2020, that it was declining in COVID, but other states like Washington, South Carolina, and North Dakota were very clearly increasing. And then we had these time series plots over time for different states as well. So as policies were enacted and as policies were changing. So in this, oh man, that plot is not so hard to see. Okay. And so California, for instance, was, in the early pandemic, the pandemic was going all over the place. And then as lockdowns occurred, COVID started declining in reproduction, and then it's potentially started going up. Really cool because early in the pandemic, these estimates were happening with hospitalization cases and deaths, and it was a really cool lagged Gaussian process model that was used to build this. So something that what you could do is you could use an HMM to say what state are we in for reproduction rates or things like that. In this case, we used a Gaussian process. So just a total aside. Let me hide this. Hide my window so you can see it. So. Yep, fun example of Gaussian processes and differing Bayesian statistics. But let's get back on track here. All right, so admittedly, we'll talk about our second topic, which is autoregressive HMMs. So for those who are unfamiliar, an autoregressive model is one that uses the previous observations as covariates for the next observations. They're particularly common in time series forecasting. You'll hear about autoregressive forecasting all the time. The reason autoregressive forecasting is nice is you don't need any covariates. You only need a single time series, and you can actually get pretty good performance by just using the observed time series and regressing it on itself. PyMC. So with any type of model, you have Bayesian estimators, you have frequentious estimators, of course, because I'm heavily Bayesian. I'll bring up the Bayesian examples, but often you'll find autoregressive models that are implemented in PyMC or other libraries, and what happens is that they don't assume any latent state. You just take the autoregressive parameters, and then you end up with some sort of noise. In this case, it looks like Gaussian noise on the outputs. Let me see if there's a nice in this notebook. If there is a nice prediction. No, this just talks about divergences. All right, well, that's no fun. Here's an example. So you have historical observations, and then you make a forecast. So this is what you'll typically see as an autoregressive model from a bunch of different libraries. But state space models, I have to say, are really cool because you can actually take the original autoregressive implementation idea, and you can then now split apart again, like we just had. You can have the state as one thing, and then you can have the prior observation, and then you can have transition probabilities and emission probabilities. So it really just takes a fairly simple model, and it expands it in a way that adds a lot of flexibility. And so we're gonna come upon this theme next week as well. But state space models, because they're so flexible, they actually end up being maybe we could say a different representation for a bunch of different models, or I could say, in another way, is a state space model is actually just a bunch of different models. So in this case, it can also be a time series forecasting model. State space models can be used for dynamical systems like spring damper mass systems and mechanical engineering. They're used all over the place, and a bunch of different models can be represented as state space model. So in this case, an AR 1, 2, 3, 4, 5, which indicates the number of lags, can be modeled as a state space model. And here is an example of that. Now, typically when you see time series forecasting problems with autoregressive models, they look like this, where you have like a traditional time series and they just increase. This is the traditional simplification that's used for a lot of time series libraries. But again, because Dynamax is, I think, such a wonderful library, you can model all sorts of stuff. This one is particularly interesting because I haven't fully understood the entire notebook yet, but my understanding is that it's modeling sort of this circular starfish thing where as you're in a state, you get pushed into another state, and then it goes this way, and then it keeps going around. I think in a clockwise manner. And the thing is that the state that you're going to be in next is dependent on the state that you were in the observations that you saw previously. So as you end up, I believe, as you get closer and closer, you tend to get pushed more into a particular state. So all that code of how the dynamics is working is in this block right here. I have not it's these two blocks. I have not read fully understood these two code blocks yet, but it is this overall thing is a really cool example of autoregressive models in general, and then showing how more than just time series plots can be modeled autoregressively, like the traditional time series. So I do plan on coming back on this. Maybe I'll talk about it a little bit more later. With 1 week, I apologize. I didn't have enough time to dig into this fully, but that is autoregressive. It looks like there's some sort of error. All right, so for folks, I'm going to try and debug my YouTube stream here for a moment. Looks like things are broken, or you might have lost me. So I'm going to check it out. Sorry about this technical difficulty. Oh, okay, stream's working. YouTube is showing me that it's not working. So, all right, if it's working, we're gonna keep on trucking along. So I may come back to autoregressive models. If anyone has questions on autoregressive models, let me know. The last topic we're going to talk about today is JAX. So JAX is a really interesting library in its own right, independent of Dynamax. It It's widely used across ML in many spaces. So state space models being one, neural nets being another. So all these large language models that you're seeing, or stable diffusion or mid-journey image generation type of things, classification, even Bayesian estimation, all can use JAX as a numerical speedup library. It's super fascinating. So what I'm going to do, today's going to be the first, but what I'm going to do moving forward is I will show you a different thing about JAX on each book club, so we sort of spread it out. That way you folks mostly get HMMs. That's the majority of the states that we're in, but we get a little bit of flavor of JAX as well. So today I'm going to talk about JAX gradients. This is a notebook I put together, and it's in the book club repo. So JAX does a lot of things. Like I said, it does numerical speedups, it does parallelization, it does actually some other cool stuff. But the one we're going to talk about today is gradients, because the fact that JAX can do autodiff and gradients is a big enabler to Dynamax functionality, but a lot of functionality for, again, neural nets and things like that as well. So starting with the basics, if we want to make a parabola, it's not too bad. Just create a function in Python. Y is a function of x, and then you return x squared. Pretty simple. And then we just create a bunch of x's. We plot that, and we get the same thing we plotted when we were probably 10 years old in school learning algebra. Later on, after we were 10, a bunch of us probably either took calculus at the end of high school, like 16, 17, or either in college potentially, and we learned this thing called derivatives, which are also known as the gradient. At the time, we learned the power rule, which meant you kind of take this 2, you put it in front, so now 2 times x, and at any point in this parabola, if we do 2 times x, we'll get the rate of change. So let's run this. Hopefully nothing breaks. Always live demos. So now this is cool. We can use JAX to do that calculation for us. We take JAX, we call .grad, and we pass it our function, which is y right here, and we get this new function which is called grad of y. And now we can calculate the gradient at any point along this curve. It's pretty neat. So because the gradient of x squared, or in Python x2, if we take the grad of that, the grad is 2 times x, just from the power rule. If we want the gradient let's say we want the gradient at 10, I'm going to run you through the super boring calculation so you're amazed. But if you do 2 times 10, we get 20, and if we take the grad of 10, we also get 20. And you can try this out on any numbers that you want. It'll all just work. So here you go. You can just you can plot this however you want. Here's the gradient at negative 4. And then if we take the gradient at 4, it flips the other way. And if we take the gradient at 2, it's this plot. And really you can get just a sense of visually of the gradient at all sorts of different spots. Now the cool thing is that for little things like this, getting the gradient is not terribly hard. Math, like, we can just look at it and do the math. But if we want to start getting gradients for things that are more complex, let's say we have a function that's a sum of sine and this exponent here, and we end up with this sort of curve. You just literally have you don't change any code. You just plug it in and you get the same thing. So now we plug in this. We can now get the gradient at like any point. So at this point, the slope is increasing really, really fast. But if we could just go back a little bit to 4, the gradient is decreasing. And it's neat that we can just take any arbitrary Python function and plug it in. So with JAX, essentially you just define a function that has numerical computation. You do use their plug-in NumPy functions like jnp.sinx and things like that. And for the most part, you can just get the gradient. It's really neat. It's really, really fantastic. Now, this is all 1D. You can also do gradients in 2 dimensions. So I won't run through the basic calculation or the code here live, but I'll just talk through it. And that we can have a function, let's say z, that's a function of x and y. And now we can get the gradient in respect to x. Or in respect to y, use a function called argnums to do that. And then you also can get the value of a function and the gradient at that point. This little thing means that if you write any numerical computation, such as the ones that are written in Dynamax, as we talked to last week, if you just do the normal math, you end up getting stochastic gradient descent like for free. So HMM learn, for instance, because it's just based on NumPy and it doesn't have gradients, it can apply expectation maximization and sort of the historical, let's say, pen and paper calculations, and it does it quite wonderfully. But Dynamax is cool because it implements the same functionality using just regular calculation, but then you also then get gradient descent. So that in and of itself is quite helpful. So when you have the original algorithm, you can still use gradient descent as another estimation method on top of it. But then, of course, because you get the gradients, you will get access to, you'll be able to solve, you should be able to estimate parameters or things using gradient descent that we couldn't do on pen and paper math, per se. I bring this up because I anticipate this is going to come up more and more as we talk about these later ones. I actually can tell right here that for this linear Gaussian SSM, they're going to use expectation maximization and stochastic gradient descent. And then I believe for these later ones, we're also going to see more and more use of gradients for estimation. It's this new layer of JAX and AutoDiff that makes it much simpler for both computational mathematicians to give us these libraries, and also for us as users to now be able to just use this library and get results. Because previously, if you implement a common filter like in the 1960s, you would have to do this stuff by hand, right? Like everybody would have to be a mathematician understanding the math. There was no API. You had to do it yourself. But these days, you don't necessarily need to know the internals of a common filter. You can just use a library and it'll do the computation for you. That is, I have to underscore that is an incredibly powerful thing that didn't exist prior to computers. So it's not even just that computers, I'm going to go on a little bit of a tangent here, but it's not just that computers can compute, right? Because humans could compute before computers. And it's not just that computers could compute things faster, which is nice. It's also that computers just take the machinery and you can hand it to somebody that doesn't know how the machinery works and they can compute from it. Versus previously, somebody had to know all the machinery to be able to compute where the Apollo mission was going to be in space. So that's my soliloquy on why computers are cool, why I think JAX is particularly cool as well, because it gives us both the computation and the gradient without even having to think too much about the math behind the gradient. The last thing I'll say is AutoDiff is popular because if you look at early neural net implementations, some mathematician had to write the gradient down by hand in the code, and so you needed somebody that could write code and could do differentiation with backwards forwards paths and neural nets pretty quickly. But once people really got into AutoDiff, you didn't need that as much. You can just pass any arbitrary function and differentiate it. There are some limitations for like if else statements, and there's some sharp bits where with, let's say, for loops and things like that for time series where this gets a little more complicated, but overall super neat. All right, let's get back to our chat. I don't think it's clear why you use JAX in a situation over PyTorch over and similar package. What did JAX add here? Chad says, which is good to be able to understand what's going on in the background. So there's going to be two sides of this debate from Luke. One side is it's going to be like a PC versus Mac thing. So I'll just say there's technical differences that you can point to are objective differences, and then there's preferential differences based off of what people feel. So we're gonna cover both. For those who don't know, real quick, there's sort of this a big generalization I can make. So don't take this as like complete fact. But you've got essentially PyTorch and TensorFlow, which are we'll call them neural network frameworks. Let's see if I can. Let's see if we can find you some code. I won't now, but I'll do it later. So PyTorch and TensorFlow are sort of maybe, let's say, these two competing libraries for neural networks, and they're generally, I have to say, their goal is to implement neural networks. So I won't. This is a big generalization, but largely they were designed as a framework to implement neural networks. And they came with an auto differentiation library included because that was very useful in neural networks. So they very much were, as you can sort of tell from this API a little bit, that they were generally meant for neural network construction. And TensorFlow is the same way. Actually, they even just mentioned that TensorFlow, Theano, Cafe, CNTK are all there. But then there's this other idea from JAX, which is more like, instead of starting with a neural network framework, why don't we just differentiate any arbitrary Python function? So instead of having a neural network library that happens to come with autodiff, what if we just had the autodiff in its own library? And that's largely what JAX does. An example where I can talk about this sort of hand wavy for now is in PyMC. We used to use Theano in PyMC3. We did not care about the neural network part about it at all. We just wanted the autodiff part of it. So we'd use Theano to get the values and the gradients. Theano sees development, and so what we have done is we have taken the actually I'll show you. We've taken the we've now taken Theano, and we taking out all the neural network parts. So we forked Theano, we've taken out all the neural network parts, and then just having the graph part, and then the gradient part goes to JAX. So we're just using PyTensor's tensor part, and then we're passing the gradient calculation to JAX. So now we're splitting apart Theano and using JAX for gradient computation, and using mostly PyTensor for the array manipulation and things like that. So to more directly answer Luke's question, TensorFlow and PyTorch come with a lot of stuff to build neural networks, and including an autodiff library, which is totally fine, and you can just use the autodiff part, and you can get down and ignore the neural network parts. JAX is not a neural network library. It is a library that happens to speed up numerical computation in arrays, and it turns out that it's really useful for neural networks as well as a bunch of other types of stuff. So you won't see on the JAX page that this is a library that implements any type of particular model or anything like that. It's a library that speeds up numerical computation. So Luke, to give you the probabilistic answer, it is not super clear why you would use JAX over PyTorch or things like that. Like, there's not a strong differentiation that you use one or the other. It's more of maybe the philosophy of how you're trying to develop your particular library, and more dependent on your use case than it is dependent on the libraries themselves. Theo asks, how come PyMC dropped Asara? So Theano was forked into Asara, and then Asara was forked by the PyMC team into PyTensor. There was just a difference in sort of design direction of what some of the folks working on Asara were doing, and then what some of the folks. Well, there was a design difference between the folks in Asara, and so admittedly, I'm on the PyMC team, so we wanted. I'm gonna word this well. There was then a question of, can PyMC stick on Asara or not? The PyMC team themselves, independent, although there's overlap, the PyMC core devs then took a vote And we were deciding between staying with Asara, doing a wrapper, forking entirely, and the majority of the devs decided that forking was the best way to go, because then PyTensor could focus on being really, really great for what we needed in PyMC, versus Asara wanting to be a much more sort of general purpose project. So all that being said, I actually am very excited about the future of PyTensor. The folks that are working on it, like Ricardo, Virgil, and the others that you see here, are absolutely just incredible people. I really enjoy interacting with them, and every time I see them put up code or change things, Siam and the rest of them, it's really, really fun, interesting to see. So here's an example of Ricardo right now fixing up the JAX dispatcher for scan. We'll talk about scan as an operator in another sort of JAX series, but this is an example of you define a model in PyMC using scan. PyTensor does a bunch of magic to expand that into a bunch of numerical computation, and then it passes it to JAX to then actually get the gradient and posterior samples. So a real nice symphony of libraries, and just a peek under the hood of what happens in full-blown open source code. I'm just going to keep answering questions as people have them. So I have to say, at this point in the book club, I have no more actual like original content to show you. Let me first talk about what we're going to do next week. Or sorry, not even next week, over the next 3 weeks. So folks who want to just drop off can see that. It of course will be on the discourse as well. But over the next couple of weeks, what we should do is we're going to go through my random state switching tabs again. We're going to talk about linear Gaussian state space models and Kalman filters. So let's go through. I'm going to say we'll be conservative. Let's go through these 3 notebooks. So Kalman filters are super neat. I'm actually really excited to dig into this particular area of state space models. It has a lot to do with rockets and object tracking and smoothing, and I'm really, really excited to dig into this portion of Dynamax. And then we also are going to be looking at I'm also going to be referring to this other book, Kalman filters in Python. This one, Kalman and Bayesian filters in Python. So this is also another fantastic textbook. As we're going through Kalman filters, you will find me referring to this a lot. So primary reading material is going to be these 3 notebooks, and then we will of course have Kevin's book, which we know and love, as one source of reference. This chapter 8, and then chapter 8.2 in particular, and then also Kalman filters in Kalman and Bayesian filters in Python. Timing wise, I again will be in New Zealand for the next 3 weeks. I also mostly be on vacation, so I'll be a little bit slower. So I think we'll shoot for another book club maybe a week or 2 in April. I may post many more async updates over the weeks. So always love the discussions that are happening in our fantastic discourse. Let's see if I can pull it up. Always love the discussions in our discourse for the HMM one. You'll see a new category here for linear Gaussian state space models. So we will see that all there. With that's we'll close out the planned portion of our book club, and let me focus entirely on the chat. Chad says, which is good and bad, able to understand what is going on in the background. Does JAX have computational advantages over other packages? So I think I think I'm reading Lars's answer already. Let's see again if this chat overlay works. Lars says, there are differences in ordering gradients chain rule, which leads to approaches called forward reverse merge differentiation. JAX uses reverse mode. Theo says it depends on what you're trying to do. Anecdotally, Uber's probabilistic programming language, it was written in PyTorch. They rewrote it in JAX and NumPy and got huge speedups. I'm also not familiar with that by now. I'll need to learn. Lars says, cool. For me, JAX NumPy and JAX SciPy save me so much time coming from scientific Python rather than ML. So, yeah, I think these Lars and Theo summed it up kind of pretty well. There's... certainly JAX has an advantage over NumPy in that it provides gradients. Like, I think that's the easiest thing to just say. If you want gradients and you're using NumPy, you can write the code to calculate the gradients manually in NumPy if you can. And plenty of people have done so, right? So there's gradients for a bunch of well-known functions. For instance, when neural networks first started started being more and more used in 2012, 2013, you would see people implement gradients by hand in neural network libraries, and certainly there's an advantage to just having JAX magically figure out the gradient for you, and that's an advantage over NumPy. Now the question then there also becomes this argument. Then we're gonna go through a couple topics here. Then there's a second layer argument: is Python better than Julia? So Julia as a language has differentiation as a first class thing that's just there. You don't have to install JAX to do anything like that. So there are constantly debates whether Python plus JAX is better than Julia. So you have that sort of discussion that occurs all the time. Open point, whether it is or is not, depending on who you ask. And then within the Python community, you have discussions of whether JAX is better than PyTorch or TensorFlow or things like that. So that also that falls into two spectrums. One is sort of where you came from as a programmer and as a person who does computation. So Theo provides a really good example here. It's more comfortable with Theo to work from JAX, and because Theo comes from scientific communities rather than machine learning, so it just makes more sense to Theo. There are people that are on the machine learning side that would argue that JAX is too low level. It's easier to just start with PyTorch or TensorFlow to get things going faster. So you have that sort of where the individual perspective is coming from folks. And then the third one, which is also an open I don't want to call it a war, but an open competition between all the different companies, is that then you have companies like, well, I work at Google admittedly, but this is me just speaking generally. Google also is developing JAX and is developing hardware like TPUs and things like that. So you saw a note here probably that no GPU or TPU found. So depending on where you're doing compute, different libraries tend to work better than others. So CPU can only do so much speed up because of the way of its architecture. GPU can do more. I'm sure you've heard about GPUs and cryptocurrencies and things like that. And then Google has TPUs, which are hyper specialized for these sorts of applications. And JAX, because it's developed by Google as well, means that the teams work together to make it really fast, like super fast. So similarly, on another topic, you may have heard that the weights for the weights from the Facebook's large language model have leaked. Their large language model is called Llama, and you can grab all the weights. The thing is that this thing is massive, so most people can't run this full model on their computer locally. There's kind of a running joke that all these A1000 GPU clusters on AWS are just like gone, just used up, because everybody is taking the weights from Facebook's model, and they're just making their own ChatGPT or Bard clones on the cloud. So the third area of contention is just computational speed up. So some could argue that JAX is better because it's fully in first class supported on CPU, GPU, and TPU, and there's a really, really tight integration because JAX is a Google library on both sides, versus if you just run PyTorch on any regular GPU or whatever, it's NVIDIA and PyTorch are not like the same sort of company. So this is, again, the third portion. So it's, I would say, in one dimension, yes, gradient aware libraries are better than NumPy because they give you gradients, arguably. The other portion is the design philosophy and where you come from, and the third is hardware software integration. All three are moving all the time. This is like these are the open sort of battlefronts of modern statistics and computational math. Oh, all right. Thanks for that additional aside. As always, let me know whether you appreciate these asides. I know they take a couple minutes, 2 to 3 minutes, where I go through a bunch of random topics. Always unsure because I can't see you folks, whether you're falling asleep behind the screen there or whether this is actually interesting, an interesting take. Sort of a combination style book club we have going on here. Any other questions that you folks have on sort of JAX, HMMs, any of that? I think we with Restream we now have a 15 to 20 second delay, so we'll pause it out here. So while I wait for questions to come in, again, I will post the next topics on our usual discourse, so you folks have them there, and I will send out email reminders sparingly to save your inboxes from too much spam. The next 3 weeks, I encourage you folks do start digging into our linear Gaussian state space models. They're really, really fascinating. I think you see how excited I am, and I'm quite thrilled to now jump into away from discrete states into continuous states. There's a lot of really neat examples here, and we'll do mostly async updates, and then I'll schedule the next time to be in April when I get back from New Zealand. We'll see how the jet lag and everything is, and how much work I did during the vacation. Admittedly, selfishly, I don't want to be on a state of I want to be in a mental state where I'm completely kind of switched off of work and enjoying the country, rather than switching between states of work and having to do relaxation. So I'm going to try and stay in a relaxation state, but make some slow progress. And then when I come back, I'll be back in my state, talking about HMMs and switching states and things like that. So the takeaway being async updates in discourse, and then I will commit to the next live stream date around the first week of April once I'm back from New Zealand and I know where I'm at. We did get some questions, so let me read through that. Can we switch between different data generating distributions from a normal distributed state to a T distributed state? So I think this is it's a really solid question. So I'm going to answer two ways. I believe there is no technical reason we can't. I don't think there's any mathematical reason or even computational reason that we can't. I'm now wondering if there is an API in this that lets us do this. Let me see. Okay, so the answer is discretely. I don't think there is a reason we would have we couldn't have an HMM that switches between different states with a different emission distribution. Let me pull this up and then I'll look again. All right. I don't think there is a mathematical or technical reason that we can't. I don't see an API in Dynamax to be able to do so. So I'm gonna try and answer your question better, Luke. I want to even see if I can find an example where there's state switching between different emission distributions that is nice and packaged that we can just share in this book club. But it's a fantastic question. I do know for sure we can switch between the subtlety is I know we can switch between states of different different linear regression. So we can switch from a state where we have maybe a regression that's going down, and then we switch to another state where a regression is going up. I think the crux of your question is whether those regressions can have different likelihoods, not just different parameterizations. And so the specific question I believe you're asking is, can we have an HMM that switches states between different likelihoods, which is like a mixture model? I will try and find an example. It's an excellent question, and I wish I had a better answer off the top of my head. Luke, do me a favor and post that in the discourse. Just throw a quick post in. Maybe you can even just copy your question and just throw it right in there. That would be great for folks async to see it. I know we have a number of HMM experts in the book club itself that aren't on this chat, aren't on this live stream, and you'll get your answer as well. Yuri says, have you seen geospatial calculations done in JAX in Google Earth Engine or otherwise? I'm going to answer vaguely yes. I don't know if I can say where, but definitely yes. I think any calculation you can do in NumPy that's done geospatially most generally can also be done in JAX. And I also know JAX is widely used internally and externally. So let me see if I can find you an external example. Let me just start Googling it. But I can, well, it looks like yes. No, that's not. That's a different JAX. Okay. I'm going to vaguely answer yes, Yuri, and you're just going to have to live with that. There's certain things I can share in this book club, and there's certain things that I have to be more careful about. Luke, would it be a mixture model? Okay, Luke, yes. One would have a mixture model in each state. Yeah, I think so. So Lars and Luke, I think we're gonna have a fun discussion in the discourse. So over the next period of time. With that, it seems like we have exhausted our questions. Of course, if you folks come up with anything, you know where to find me with on the discourse or emails or things like that. We're a little bit over an hour again, so thank you for sticking with me with that as well. And with that, as always, I hope you enjoy your Sundays. Hope you have a fantastic remainder of the weekend, however many hours that is. And this time, I hope you have a fantastic month ahead. I won't be seeing you for quite a while here, at least synchronously. So thanks for sticking with the book club. Nice to see you all, and I will see you next time.